Okay, thank you. Good morning, everyone. How are you all doing? Okay. You seem to be in a singing mood. All right. So, so we will do a quick recap. We won't really use anything from yesterday. So today's lecture, the things that actually need following will be independent from yesterday, right? Except for some definitions which I'll recap anyways, right? So let's take an example. Right, so here's a two connected three regular graph. Three regular means every vertex has three edges incident at it. Degree is equal to 3 for each vertex. And two connected, there are multiple ways of looking at it. One way of looking at it, the way that I actually follow, is that between any two vertices, there are two internally disjoint paths. Internally disjoint means that they don't have anything in common except for the two vertices because they are between those two vertices. Another way to think of internally disjoint paths, well, the internally disjoint paths, the union is just a cycle. So, for any two vertices, they belong to a common cycle. This is the same as saying that there are two internally disjoint paths between the two vertices. Do you agree? Yeah? Two internally disjoint paths, their union is a cycle. And if there's a cycle connecting two vertices, then you have two internally disjoint paths. So it's the same. Yeah? And so the statement is saying that every two connected three regular graph has a perfect matching. This is something we proved yesterday using Brooks Theorem. You don't need to know what Brooks Theorem is. In case you were not there yesterday, don't worry about it. What's a perfect matching? That you need to know. Here's what a perfect matching looks like. In the orange graph, every vertex has degree 1. Keep all the vertices, but take only the orange edges. Right? So, a set of edges is a perfect matching. If for every vertex, this is the edges incident at the vertex. Partial V is edges incident at V. At each vertex, this is equal to 1. In other words, it is a spanning one regular subgraph. Yeah, every vertex is degree 1. Yeah. And if you relax this to be either 0 or 1, what you get is a matching. Yeah. So here the orange one is a perfect matching, whereas the yellow one is a matching that is not perfect. Yeah. Okay. And we also proved that not only do such graphs have a perfect matching, they have a stronger property, which is that for every edge there is a perfect matching containing that edge. Yeah. Okay. Alright. And today what we will prove, one of the things we will prove, is that the edge chromatic number of any three regular graph, irrespective of whether it is two connected or not, that number is either 3 or 4. So what's the edge chromatic number? Is the minimum number of colors you need to color the edges so that any two adjacent edges get distinct colors. Right? For example, in this graph, I can take the orange perfect matching, I can take the blue perfect matching, and the rest of it is the third perfect matching, the pink edges. And now what we have is a pink, blue, orange coloring. That's 3 colors. Therefore, this graph is 3 edge colorable. Clearly, if you have a vertex of degree k, you need at least k colors. So, for a 3 regular graph, 3 edge coloring is the best you can do. Right? That's the minimum number of colors you need. What the theorem is saying, which we will prove today, is that you don't need more than 4. This is interesting if you consider a 3 regular graph that is not 3 edge colorable. For example, the Peterson graph is the smallest 2 connected 3 regular graph that is not 3 edge colorable. And what you all can try, maybe you can try now, see if you can use 4 colors to color the edges. Give it a shot. Use 4 colors to color the edges of the Peterson graph. Yeah? Good. Good exercise to wake up. Got it? Yeah, okay. Got it? Okay. Got it? Good, right. Okay, cool. Alright. Keep working. Alright. Alright. So there are many different 4H colorings. This could be, for example, one of your colored classes. But as I said, there are lots of different 4H colorings. I don't know how many different, up to permutation of colors. But yeah, you can definitely choose this one as one of your color classes and complete it from here, for example. Yeah, now you have two odd cycles, the inside 5 cycle and the outside 5 cycle. And you can see that an odd cycle is 3H colorable. Yeah, an odd cycle actually requires 3 colors for the edges to be colored, or for the vertices, because they are not really different. So therefore I can use 3 colors in the inside cycle, I can use 3 colors in the outside cycle, the same 3 colors, because they are anyways vertex disjoint. So I'm done. Right? I can take any 3H coloring of this 5 cycle, any 3H coloring of that 5 cycle, using the same 3 colors, and that will give me a 4H coloring of this fellow. Yeah. Of course, what is more interesting, which we did yesterday, is that this graph is not 3H colorable. Right? So that we did yesterday. Those who were not there yesterday, you can try it later. Here's an exercise for you. Prove that Peterson graph is not 3H colorable. In other words, the edge chromatic number is actually 4. Yeah. Okay, so the way to do this is to focus on this set of 5 edges, focus on this cut, and try to proceed from there. Okay, we did this yesterday, so I'm going to skip it. Right. By the way, we're recording everything, so if you missed yesterday, you can just watch it on my YouTube channel. 2 of them are already posted, the third one is not there yet. Yeah. Okay, so is the general concept clear? Yeah. So now here's a question. If you consider an edge coloring of a graph, right? So what do I mean by an edge coloring? Color the edges so that any two adjacent edges get distinct colors. If you consider any edge coloring, what does each color class look like? Each color class is a what? By each color class, I mean the edges that receive a particular color. So if I look at the yellow edges, here is an edge coloring. If I look at the orange edges, matching, right? You all agree? In any edge coloring, any color class is a matching. Because any two adjacent edges should get different colors. Therefore, the edges that get the same color, they are pairwise non-adjacent. Right? That's just definition of matching. Right? Yeah. So, therefore, the study of edge colorings is intimately connected to the study of matchings. In any edge coloring, each color class is a matching. You all agree? Yeah? Okay. Need not be perfect. In a 3 regular graph, if you have a 3 edge coloring, then the 3 color classes are just perfect matchings, as we discussed yesterday. Right? But in general, if I give you an edge coloring of a graph, each color class is a matching. That's all we can say. Right? Okay. Alright. Since we just discussed this, by the way, can we go to vertex colorings for a moment? Yeah, you all know what vertex colorings are, right? You color the vertices, any two adjacent vertices should get different colors. So in a vertex coloring, what are the color classes? What does each color class correspond to?
Independent set.
Independent set, right? Which I will call a stable set. Is that right? Okay. So let's also note that down. In any vertex coloring, each color class is a stable set, also known as independent set. Yeah? Okay? Alright, we'll find this useful later. So before we go to this, I want to make a couple of comments. Also because some of you were asking me about what is the kind of research I myself do. I work on perfect matchings for a living. And there's a lot of problems on perfect matchings that are yet to be solved. And that will always be the case, because welcome to mathematics. Right, so here's a book that was published in 2024 by Lucchesi and Murthy. And Murthy being my PhD advisor. And yeah, this book is basically full of open problems as well as a lot of theory. So just as an example of some recent research we did, I'm not going to really talk about this, but just since some of you are curious, so let's look at this statement which we proved yesterday. In a 2-connected 3-regular graph, each edge participates in some perfect matching. This is Schoenberger's result from 1934. Yeah. Therefore, in 1934, let's rewrite this. Instead of some perfect matching, let me write down at least one perfect matching. Is that okay? Yeah. Good. Because this way of writing leads to a natural question. What are those edges that belong to exactly one perfect matching? Yeah? What are those edges? In a 2-connected 3-regular graph, what are the edges that belong to exactly one perfect matching? Let's do a quick example. Can we count the number of perfect matchings in this graph? I'll give you a hint. Here's the hint. Count the number of perfect matchings in this graph. If you have counted, just raise your hand and I'll come and talk to you. Right, so count the number of perfect matchings and pay attention to this cut. This is a cut of the graph. And think about the intersection of any perfect matching with this cut. How much can that be? We discussed this yesterday, but if you are not there, you can think about it freshly. Right? So what is the intersection of any perfect matching with this cut? What can it be? And if you think about that, then you will easily be able to count the number of perfect matchings. Okay, anyone else? Right, so this is the three edges, these three edges. Let's call it C, 1, 2 and 3. Observe that the intersection of any perfect matching with this cut is odd. Convince yourself that this number is an odd number. Yeah, there is odd number of vertices on the left side, odd number on the right side. Therefore, an odd number of them have to be matched from the left to the right. And if this is odd, then it has to be 1 or 3. If it is 1, then you have the three perfect matchings that are shown to you in pink, blue and orange. Those are the three perfect matchings whose intersection is 1. If you allow intersection 3, well, that just means you get the fourth and the only remaining perfect matching. Yeah? So therefore, since the intersection has to be 1 or 3, there is 3 of the first type and 1 of the second type. Right? That's it. Yeah. Alright, so now that we have drawn all the perfect matchings, can you tell me the edges that belong to exactly one perfect matching? Yeah, can you see all of that? Yeah. Now you have all the perfect matchings at you, staring at you. So you can just look at them and tell me what are the edges that belong to exactly one perfect matching.
Those that do not intersect C.
Yeah, the edges of the triangles. Right? The edges of the triangles, they are the only ones which belong to one of these 4 perfect matchings. The edges of the cut C, they belong to 2 perfect matchings. Yeah. So that's a question one could have asked. What are those edges that belong to exactly one perfect matching? Yeah, this question one could have asked all the way in 1934. Interestingly, nobody did or nobody cared to, because there had other things going on in life. And finally we did, because we didn't have much going on in life. And we answered it recently, right? So interestingly what happened is, just as I and Narayana, one of my master's student, we were working on this problem. Before Narayana, there was an intern, Kalyani, who had also been working on it, but she was working on it for a shorter period, because intern. And Narayana did his entire master's on this. So we made significant progress on this problem. Without going into details, you can check out to my YouTube video by Narayana, not by me, on my YouTube channel. So better version than what I would have done. And that explains what the results we got. So interestingly, the same time that we were jobless, there were some people in Europe, 5 people, who were also jobless. And they also obtained the same results. We also had the same results. Interestingly, our techniques were completely different. And one of them, Giuseppe Mazzucolo from Italy, he actually said in the online meeting that your techniques are way more general and you should be able to generalize your results to a larger class of graphs called R graphs. So they are R regular graphs. R graphs. They are R regular graphs with a certain connectivity condition. If you put R equal to 3, you will get exactly this, 2 connected 3 regular graphs. And that's exactly what we did. So we collaborated with one of them, David Mattiolo, who is a postdoc in Belgium, and we were able to generalize all of these results that we had to R graphs. Right? So this is basically, I mean, the main contributor here is really Narayana. He's the one who actually was the engine of the work. Right? So anyway, so that's something that we did recently. You may ask, what does it mean? Like, what exactly do we mean by this question? So you can ask for bounds. Is there an upper bound or a lower bound on the number of such edges? We call such edges solitary edges because they belong to exactly one perfect matching. So it turns out for two connected three regular graph, the upper bound is n by 2, where n is the number of vertices. So if your graph has 100 vertices, there is no more than 50 solitary edges. However, for three connected three regular graphs, you bump up the connectivity and you get something more. The answer is 6. There are no more than 6 solitary edges in any three connected three regular graph. And now the question is, which are the graphs that have 6, 5, 4, 3, 2, 1, as I said, jobless. So we try to answer all of these. We answered them for 6, 5, 4 and 3. For 2 we don't know the answer, for 1 we don't know the answer, and for 0 we don't know the answer. Right? Anyways, so that's basically what we did. There is some 50 pages, but most of it is theory, which is what I really like. So there's a lot of theory that we build, which allows us to generalize our results to R graphs. And problem solving is just a corollary of theory building. Right? So that's how it is. So anyways, but I don't want to go into this because I want to do this. Then I want to focus on the more classical results. If you're interested, you can just check out the YouTube video by Narayana. Right? Any questions, concerns regarding this? Observe that this fellow has 6 solitary edges. Turns out for 6 there are only 2 graphs actually. If you want the answer for 6, it's not too difficult to prove that the only graphs with 6 solitary edges, 3 connected, 3 regular, are K4 and the triangular prism. 5 is only one graph. 4 and 3, there's actually infinite families. Things become more interesting then. Yeah. Okay. Alright. Any questions, concerns regarding any of these things? Yeah, so feel free to ask anything because once we move on to this, then we won't come back to these things.
What is the unique 3 connected 3 regular graph on 5 vertices?
Oh, you want to see the one with 5 solitary edges? It's a beautiful graph called the bicon. So here is a nice drawing of the bicon. It actually plays an important role in the theory. So if you pick up this book, it has a bunch of results where the bicon is a special graph. Of course, the most special graph is the Peterson graph. But yeah, so this is the bicon graph. The only solitary edges, you can figure it out if you like.
For the two connected three regular graph, what is the lower bound?
Lower bound is, we mainly have upper bounds. So the lower bound, you could have 0 solitary edges. So that's a good example, Peterson graph. In the Peterson graph, there are 6 perfect matchings, and every edge belongs to 2 of those 6. We'll come back to this point. The point is that there is no solitary edge. So in general, a 2 connected 3 regular graph, or even a 3 connected one, may not have any solitary edges at all. Yeah. So the interesting question then becomes the upper bounds. Any other questions, concerns? But this brings us to one more interesting point. As I said, the Peterson graph has 6 perfect matchings, and every edge belongs to exactly 2 of these 6. Here is one of the most famous conjectures in graph theory. In any 2 connected 3 regular graph, there is a set of 6 not necessarily distinct perfect matchings, so that every edge belongs to exactly 2 of these 6. Yeah, let me write it down. In any 2 connected 3 regular graph, maybe I'll call it a collection since I'm allowing repetition, I don't know. In any 2 connected 3 regular graph G, there exists a collection M1, M2, M3, M4, M5, M6 of perfect matchings such that each edge lies in exactly two of them.
Each edge of the graph?
Yes. Each edge of the graph lies in exactly two of these 6 perfect matchings. And it is important to note that these are not necessarily distinct. So I have a question for all of you. Is one of these two cases easy? We will prove that the edge chromatic number of any 3 regular graph is either 3 or 4. Is one of these two cases easy? Can you already prove the result for one of these two cases?
Oh.
For one of these two cases, can you already see why the result is true? Why the conjecture is true? Either the graph is 3 edge colorable, if not the graph is 4 edge colorable. And what is 3 edge colorable? What does it mean to be 3 edge colorable? It means that there are 3 disjoint, pairwise disjoint, perfect matchings. M1, M2, M3. So M1, M2, M3, M1, M2, M3 is the answer. Yeah? So we are done for this case. The difficult case is when the edge chromatic number is 4. These are called snarks. So if you solve this problem for snarks, you are done. And this is the famous Baird-Fulkerson conjecture. Yeah, the same Fulkerson from Fulkerson Price. Yeah, so this must be open, I don't know, Baird and Fulkerson, I don't know, 1960s or 70s. So do the math, open for 50, 60 years or something. Yeah, of course, I don't know whether this 6 has anything to do with our 6. I don't think so. The our 6 being the at most 6 solitary edges. I don't know about it. I don't know why they are both 6. Of course, the Peterson graph is very interesting because, as I said, the Peterson graph has exactly 6 perfect matchings such that every edge belongs to exactly 2 of those 6. So, Peterson graph is really sort of an extreme example from the point of view of Baird-Fulkerson conjecture. Yeah? Okay? Any other questions, concerns, discussions? Okay, so yeah, so this would, I would say, this is probably one of the biggest open problems in not just in matching theory but also in graph theory. Okay, so that's something about modern research and all that, and stuff we cannot prove so far. So what we will do now is we will switch to this. We will prove that every 3 regular graph, the edge chromatic number is either 3 or 4. Okay. In order to prove this, we will go to vertex colorings, and today the focus will actually be on vertex colorings. Right? We will prove this as a corollary of a result in vertex colorings. Right? Okay. So if there are no questions or concerns, I will erase this part, and I will go to vertex colorings. At some point, I will erase all of this too. I suppose I can erase the definition of matchings and perfect matchings. Yes.
We went to vertex coloring to edge coloring for photo. Why are we again going back to vertex coloring?
Good.
We just
Yeah. So, so that's actually a very interesting point. So one of the common criticisms of graph theory is that these people just invent problems and then solve them, right? Which is of course all of mathematics at some level. because of course everything is invented at some point. Yeah, so one of the criticisms is that, oh, they study edge colorings, they study vertex colorings, they study face colorings. Why are they studying all these different things? Can't you just reduce all of them to one and then just study one? The answer to that is actually no. So it is not true that in order to solve edge coloring problems, one can focus only on vertex colorings or vice versa. Yeah. So I think this will become clear once we do this part, and I'll comment on that again, right? So let's see how we will actually solve this using a vertex coloring result, and then I'll comment on this point again, right? But that's a very good question, so thanks for bringing it up. Yeah. And what we did yesterday, so we started with the 4-color conjecture, which was actually for face colorings. It was about map colorings, right? And then people observed that you could actually transform it to vertex colorings because of plane duality. For any plane graph, you can draw the plane dual. And using that, you can go from face colorings to vertex colorings, right? The advantage of vertex colorings over face colorings is that you don't need an embedding. You don't need a drawing anymore. To talk about the faces of a graph, I need a planar drawing. Otherwise, I cannot talk about faces of a graph. A graph is only vertices and edges, right? So that's the advantage of going from face colorings to vertex colorings. Now this, what happened is, because people were not able to make progress on the 4-color conjecture, people started looking for equivalent formulations. One such equivalent formulation was given by Tate in terms of edge colorings, which said that every planar 2-connected 3-regular graph is 3-edge colorable, which is the same as saying that there are no planar snarks in the world. This is the same as the 4-color conjecture. Okay. And of course, Tate gave this equivalent formulation, which itself is beautiful, aesthetically pleasing and all that. But so what? We were not able to prove it. I mean, Tate actually convinced themselves that they had a proof of this statement, which they did not. Right? It was a false proof, as figured out by Peterson. But there is an interesting thing that happened. This equivalence of vertex colorings and edge colorings in the case of planar graphs, this is actually a special case of a more general theory called flows. This is not your network flows. These are called nowhere zero flows on graphs. So if you open a textbook on graph theory, you are likely to find a whole chapter on flows. And that is actually a generalization of Tate's observation. But unfortunately, I don't have time to talk about flows. In fact, I don't even have time to talk about flows when I teach a graph theory course. That's the amount of content I have to cover, or I want to cover. So yeah, but there is a very beautiful generalization of this thing that we discussed yesterday, the Tate's equivalence, right? So what you do is you give labels to the edges. These labels come from a group, and you have some conditions on this labeling, and that turns out to be a whole area of research in graph theory, where there are some of the biggest open problems in graph theory. One of them is called Tutt's 5-flow conjecture. I won't define the conjecture, I don't even think I can right now. But yeah, there are some very big open problems in this area. Unfortunately, this area is very underrepresented these days, especially in India. I don't think there's anybody working on flows. Yeah. Yeah, but anyways, we'll come back to this point once we go through this. Yeah. So let's prove this result using a vertex coloring result. Okay. So let's kind of switch our attention to okay. We'll start from the basics. Alright, forget everything else if you can. So let's think about a sort of easy upper bound on the minimum, on the number of colors you need to color any graph. Let me see, do I need any conditions? No, no conditions. Right, I want an easy upper bound on the number of colors required to color the vertices of a graph. Number of vertices is the most trivial upper bound, great. N, clearly N works. Okay? Okay, so now we'll try to get something better than N. Yeah?
The highest degree of any vertex.
delta, maximum degree. Is that right? Okay. Is that an upper bound?
Delta G plus 1.
Delta plus 1. Delta plus 1 or delta? Can you think of a graph that requires delta plus 1 colors?
Connected. I mean, completely connected.
What is completely connected?
K is something.
K is something. K5. How many colors does K5 need? 5. And what is delta? 4. So delta plus 1. Okay? So, okay, let's write it down. Complete graphs require delta plus 1 colors.
Maximum degree.
Complete graphs require delta plus 1 colors. Here delta is max degree. Yep. Okay. Any other class that requires delta plus 1 colors?
Odd side.
Odd cycles. Odd cycles require how many colors? 3. Yeah. Delta is 2. Yeah. Okay. Odd cycles require delta plus 1 colors.
Edge coloring.
Vertex colorings, right? You're talking about vertex colorings. So, of course, odd cycles, even the edge coloring requires delta plus 1 colors. Because, well, what's the difference between edges and vertices in an odd cycle or in a cycle? Okay. So, are there any other graphs that require delta plus 1 colors, or are there any graphs that require more than delta plus 1 colors? Does anybody require more than delta plus 1 colors? Okay, that needs a proof, right? Let's prove it. Okay, don't blurt out the answer. See if you can think about it. So DIY. For any graph G, its vertex chromatic number, or also known as chromatic number. So generally when people say chromatic number, they mean vertex chromatic number. Its chromatic number is at most the max degree plus 1. Alright? See if you can prove it. And if you have figured out something, raise your hand and I'll come and talk to you. Maybe write down something so that I can also read what you're doing. Okay, anyone else? Yeah.
You can start it anything.
Anyone else? Yeah. make sure that your argument makes crucial use of this number, right? I mean, at some point you should be able to say why delta plus 1 works. If you replace delta plus 1 by delta, it should fail. So, okay.
What is special in computers? Okay, I know the theorem.
Right, so here is a hint. Just think you have a palette with delta plus 1 colors. I've given you a palette with delta plus 1 colors. Just start coloring the vertices and see where you get stuck. Try to create a situation where you would get stuck. Or if you're not getting stuck, then just try to think why you're not getting stuck. What is so special about the palette that allows you to not get stuck?
So we change this to
No, you shouldn't change anything. Don't change anything. Once you've colored a vertex, you should never be required to change it.
I will say,
So if your argument currently requires changing, let us simple argument. Just take your favorite graph and start coloring with delta plus 1 colors and try to see where you get stuck. And if you're not getting stuck, then just try to think why you are not getting stuck. And that should basically lead you home. While you think, I'll just get some water.
These two graphs with delta plus 1.
You know the proof right away. You know guys as in delta plus 1.
No, less than delta plus 1, I know from general. I'm saying Brooks Theorem.
That you have
I know, Brooks is a harder one, no?
What's the hardest?
Brooks is harder. You guys put Brooks Theorem in 20 minutes. Man.
Basically, this is forgetting.
These are the only two graphs with delta plus 1.
Alright, yeah.
Everything else is the same.
How do you put that in 20 minutes? Is it hard as this guy? Have you read the proof?
No, it's a 9 out in a Z using.
Where? I mean, that's. I don't know. He's going to ask you.
How do you know Brooks Theorem in 20 minutes? It's a 9 out in a Z unit, it would 20 minutes. CG.
I mean,
I was planning to take that, but that should be the best. That's Brooks Theorem and class should make help.
The reason that I don't know is because you're completed
I'm not with that.
why? Maybe like you didn't have the one in the right.
I'm sending you.
I see what it is today. If you get stuck, then that's the only option you have.
Bro, I just saw the Brooks Theorem in the
It
range.
looks like. I don't know.
What? This is random very good. Anybody can post stuff.
No, the proof is not this. There are two cases. I signed up.
I see it.
What is there are three cases? There are two cases.
Okay, तो आने ना so let's think what special about these two brothers thanks don't need to spoil
Bro, how is that a major spoiler?
the spoiler
Less equal to 2 is our first. Big deal, bro.
Why would you spoil that for the whole movie?
so why are you spoiling 1 minus 1 to 2 don't spoil
Yeah.
He's let him take
I
60 pages
forgot
to
to
do
equal
it.
to 1. Oh no, I spoiled it for you again.
You should let him take 360 pages to do it.
20 base cases later.
I guess I'll give a small hint. Consider any ordering of vertices. V1, V2. Just consider any ordering and start coloring. You have a palette with delta plus 1 colors. Right? This is color 1, this is color 2, this is color delta plus 1. This is your palette. And think of giving this fellow a color, then think of giving this fellow a color, and so on, and try to see when you would get stuck. And if you feel that you get stuck, then try to resolve that. If you feel that you never get stuck, then try to figure out why you are never getting stuck. Every time I go to a vertex, there are some vertices in the neighborhood that are already colored, and there are some that are not colored. Just think about this, right? And if some of them are colored, how many colors can they use? The ones that are not colored, they don't bother you. They will come later in the order. Right? So I'm coloring in the order. I will first give a color to V1, then to V2, then to V3, and so on. So whenever I reach a vertex, I look at the already colored neighborhood. How many colors can they use? At most delta, because the maximum degree is delta. How many colors do you have? So there is a free color. So you can give the free color to this fellow. Whenever I am at some vertex, Vi, I look at the neighbors. They use at most delta colors. I have a palette with delta plus 1 colors. I'll give the delta plus first color to this fellow, whichever is remaining, right? I don't even need to specify. I don't even need to order this in any way or this in any way. Right? Some of you are trying to order in a certain way, first book the maximum degree vertex and all that. None of it matters. Take an arbitrary ordering and observe that at every vertex you have a free color. You color, you're done.
Like it was made in arbitrary colors, and then if any
You have taken an arbitrary color.
and if there's any failing pattern, we can just switch out one of them.
Yeah, but that needs more thought. So so you are starting with an arbitrary coloring, which may not actually have the property you want, and then you are trying to fix it. That might be possible, but all I'm saying is that this is way simpler. Right? You don't need to do any switches at all. Just consider an arbitrary ordering and just color, and observe that you will never run out of colors because your palette has delta plus 1 colors. Right? You always have a free color. Yeah, do you all agree this works? This is called the greedy heuristic. Too fancy a name for something like this. But anyways, this is called the greedy heuristic. So, are you all convinced? We prove this? Yeah? Shall I put a QED? Is it okay? Alright, yeah. So now what we will do is, we will use this result to prove this. For any 3 regular graph, the edge chromatic number is 3 or 4. Okay? Think about how you would do that. How would you use this vertex coloring result to prove an edge coloring result? If you have already seen certain concepts, that might help you. If you haven't, we'll try to come upon them together. Yeah, so if you are thinking in the direction that maybe I should construct another graph, that is the correct direction. Right. So, right. You want to transform an edge coloring problem into a vertex coloring problem. Yeah. So, okay, good. Actually, I missed a point. Yeah, actually proving that it is 3 or 4 needs more work. Prove that it is 3, 4 or 5. I forgot that I had not mentioned the theorem yet. Yeah, so instead of doing 3 or 4, try to prove that it is 3, 4 or 5. Good. Okay, then we'll come to 3 or 4. Yeah, for that I need to tell you something else. Okay, so if you have gotten to 3, 4, 5, we want to go to 3, 4, but that needs one more result, which I haven't stated, which is what we will actually prove. That will be the main focus. So it turns out that there's a question that arises here. What are the graphs that actually require delta plus 1 colors? Yeah? And by the way, for vertex coloring, we may restrict ourselves to simple graphs. You all agree? For vertex colorings, this really doesn't matter.
Oh, yeah.
Yeah? Okay. So you may ask the question, what are the simple graphs that require delta plus 1 colors? Clearly we know complete graphs do and odd cycles do. Turns out they are actually the only ones amongst the connected ones. If it's not connected, then you can think about it. So what we will prove,
Not heuristic, empty, independent.
we will prove this result called Brooks Theorem. For every simple connected graph, the chromatic number is at most delta plus 1, and equality holds if and only if the graph is a complete graph or an odd cycle. Okay. Either it's a complete graph Kn or it is an odd cycle C2k plus 1. Yeah. Okay. So now what you can do is you can assume Brooks theorem, which we haven't proved yet, and you can try to go from 3, 4, 5 to 3, 4. Okay, this was the missing piece. So see if you can now do that. And if you want to discuss 3, 4, 5, let me know. I'm happy to come and talk about that. In particular, I hope you all have arrived at the point that you need to construct another graph from the original graph, right? If you are stuck with that, let me know, right? So how do you construct the new graph from the original graph? Does anybody want to explain it? Go ahead.
So you consider a new graph where the vertices of the graph denote the edges of the field.
Okay, so for every edge of the original graph, you will have a vertex in the new graph. Yeah.
And you connect.
And somebody can explain the adjacency? Okay.
You connect two vertices of the new graph if the corresponding edges in the original graph shared a vertex.
Exactly. Two vertices in the new graph are adjacent if and only if the corresponding edges were adjacent in the original graph. Is that correct? Yeah. Okay. This is generally called the line graph of a graph. Right? So for any graph you can define this fellow. Unfortunately it's called the line graph. But anyways, not a big deal. Right? And now you observe that edge colorings of the original graph simply correspond to vertex colorings of the new graph. Is that correct? Right. And the point is that because your original graph is 3 regular, every vertex of the new graph has at most 4 degree. Yeah. In the new graph, every vertex in the line graph, every vertex has degree at most 4. Therefore, we can color the vertices using delta plus 1, which is at most 5 colors, and that would be a 5 edge coloring in the original graph. So therefore, 5 definitely works. Therefore, the edge chromatic number is 3, 4 or 5 because definitely it is at least 3. It's a 3 regular graph. Yeah.
Why is the degree at most 4? Shouldn't it be exactly 4 for all?
Oh yeah, exactly. Yeah. So the point is, every vertex has degree exactly 4. Yeah, that's true. Good. Okay. So therefore we get to 3, 4, 5. And now the question is, how do you eliminate 5? We'll use Brooks theorem. Yeah, so assume Brooks theorem and do this. So yesterday's focus was TUT. Is that fair to say? Yesterday's focus was TUT. And today's focus is Brooks. So let's talk about TUT and Brooks. So, how many of you have heard of Blanche Descartes? Anybody? This is not a real person. Wasn't a real person. So Blanche Descartes was a collaborative pseudonym used by the English mathematicians Leonard Brooks, Arthur Harold Stone, Cedric Smith, and Tutt. The 4 mathematicians met in 1935 as undergraduate students at Trinity College, Cambridge, where they joined the Trinity Mathematical Society and began meeting together to work on mathematical problems. So there were 4 undergrads who used to publish under this pseudonym, and they solved a bunch of very beautiful problems, and some of them went on to become very famous mathematicians. Bill Tutt was actually a chemist by training, and then became a mathematician. That wouldn't fly in India even today. Just saying. And when Bill Tutt was doing graph theory in 1940s, Great Britain, England, whatever they call it, people would ask, people would tell Bill Tutt, other mathematicians would mock Bill Tutt, why are you working on these 1 simplices, you should work on k simplices or whatever. Bill Tutt kept doing graph theory, and Bill Tutt is one of the main reasons why graph theory is a reasonably respectable subject in most countries, unfortunately not in India. Anyways, not yet. Yeah, anyway, so that was the situation back then in UK. Unfortunately, we still have the same situation here. Right, so, yeah. Yeah.
So since the line graph is 4 regular, so it can't be a cycle, so it has to be K5. And then you end up with any 2 edges shared.
Yeah. So does everybody kind of see how to use Brooks theorem to make progress now? Right. The point is you need delta plus 1 colors only for, it's basically the second part of Brooks theorem that we really need, which was missing. Equality holds if and only if the graph is a complete graph or not cycle. So if the line graph is not a complete graph or not cycle, anyways you are not going to need delta plus 1 colors, as we will prove. Right. Therefore the only case we need to care about is when the line graph is a complete graph or not cycle. But we already discussed that every vertex has degree exactly 4. So to be a complete graph or a not cycle, it has to be K5. Now you just need to come to a contradiction. There are many ways to do it. I won't discuss that, right? So just convince yourself that for any 3 regular graph, the line graph is not going to be K5. Yeah. You can do it whatever way you like. If yeah, it's okay. Yeah. So if it's not K5, you're done. Finish. Okay. Alright. So the point of vertex colorings and edge colorings. If every edge coloring problem could be converted to a vertex coloring problem and vice versa, then we would only study one of the two. And we would probably stop studying the other. Of course, even then, the other one could give you insights, which the other, one viewpoint could give you more insights than the other viewpoint, right? So what we did here is we converted an edge coloring problem to a vertex coloring problem, right? And in order to do that, we considered the line graph and we studied the line graph and we made some conclusions about it, right? But observe that you can't do the other way around. How would you convert a vertex coloring problem into an edge coloring problem? How do you convert a vertex coloring problem to an edge coloring problem?
Take the vertices and take
Does it work?
And you
Because
define
there-
some version of a graph wherein edge
It would be nice to have an anti-line graph.
wherein edge can connect more than 2 vertices.
Those are called hypergraphs. But then you are changing things quite a bit, right? Right. So that's a problem. You can't convert a vertex coloring problem into an edge coloring problem. In particular, not every graph is a line graph of some graph. That's another interesting point to note. It is not true that every graph is a line graph of some graph. In fact, there is a characterization of graphs that are line graphs of another graph, and that is not the set of all graphs. So there are graphs that cannot be, that are not line graphs for any other graph. So, right? So anyway, so the point is that you can't convert a vertex coloring problem, at least we don't know as of today, how to convert a vertex coloring problem into an edge coloring problem, right? Yeah. And therefore vertex colorings receive their own attention and edge colorings continue to receive their own attention, right? Because there is no direct equivalence in some sense. Of course, there are cases like what we saw right now where we were able to use a vertex coloring result to make progress on an edge coloring problem. So point in case here. Here is a statement for all graphs. This is a Gupta theorem that I mentioned yesterday. Every graph, the edge chromatic number for every simple graph, the edge chromatic number is either delta or delta plus 1. This sounds very much like Brooks theorem, but there is no known way to go from one to the other. Gupta theorem, I don't know how to prove using vertex coloring results, and I don't think it is known in general. So for edge coloring, you have a similar result as Brooks theorem. It sounds similar. The edge chromatic number is delta or delta plus 1. In vertex coloring, it is actually much more interesting. The upper bound is delta plus 1, and it is attained only for odd cycles and complete graphs. But the lower bound could actually be very low. Right? So the range of edge vertex chromatic numbers is much larger, whereas for edge chromatic number, the range for a simple graph is just delta or delta plus 1. And if you have heard of NP complete problems, deciding which one is actually NP complete, which basically means that we don't know of any quick algorithm to tell by looking at a graph whether its edge chromatic number is delta or delta plus 1 for a simple graph. Yeah.
So can you show the construction for the case of 4 because of what you want to find? Like I understood. Can you show the construction
For 4. By construction, you mean how to rule out the K4, K5?
Oh no, K5 I know it.
Okay.
For example, if you take a regular graph,
Yeah.
like 3 regular graphs,
Okay.
how like a particular regular graph that has a number of edge.
Peterson graph.
Can you show?
Yeah, sure. So, this is the smallest two connected three regular graph that requires 4 colors. Yeah. And if you want to prove that, pay attention to this cut. This is something we did yesterday, so I'll just tell you briefly. Think about this cut and think about each perfect matching. What is the intersection with this cut? And from here you can prove that it is not 3H colorable. Is that what you were asking?
Yeah.
Okay. Cool. Right. Anyway, so where was I? NP complete. Yes, good. Thank you. Yeah. So anyway, so deciding whether a simple graph requires delta colors or delta plus 1, we don't know how to tell that quickly. Like you can't write a fast computer program that will tell you whether the edge chromatic number is delta or delta plus 1, at least as per the current state of art. And in fact, people largely believe that it may not be possible, which goes into NP completeness and all that stuff. Okay? Any questions or concerns before we continue further? So the next goal is to prove Brooks theorem. So we are going to say a complete goodbye to edge colorings, matchings and all that. And for the rest of today, we are going to focus only on vertex colorings to prove Brooks theorem. Yeah? How much time do we have in this session? 20 minutes more? Okay. Let's get started. That's the result. We have already proved that the chromatic number, the minimum number of colors required to color the vertices, is at most delta plus 1. We did that using the greedy heuristic. And we have also observed that for complete graphs and odd cycles, we need delta plus 1 colors. What remains is to show that these are the only fellows for whom we need delta plus 1 colors. Yeah? Okay. So, let's think about the greedy heuristic again. We are coloring the vertices in some order, right? But of course we chose an arbitrary order. We chose any arbitrary order and we just said that, hey, since the palette has delta plus 1 colors, you will always have a color whenever you reach a vertex and you will just give that color to that fellow. Yeah? And that is also true for the last vertex. Right? Even in the last vertex, at most delta are used by the neighbors. So I'll give the delta plus 1 first color to this fellow, whatever remaining color. Okay. Let us make an observation about complete graphs and odd cycles. And actually odd cycles are more interesting than complete graphs in some sense. What would you do to color an odd cycle? How would you, if I give you an odd cycle and I ask you to color it using 3 colors, what is the most natural thing you would try? You will keep alternating, right? Red, blue, red, blue, red, blue, and then you reach a vertex whose one neighbor is red and the other neighbor is blue, and now you choose the green color to give to this color. Okay. That's actually interesting because what we just observed is that there is the coloring using delta plus 1 colors where one of the color classes has only one vertex. There is a coloring of any odd cycle using 3 colors where we use only one vertex for a particular color class, the green fellow. Yeah. Of course, this is also true for complete graphs, but you can see why it is not as interesting for complete graphs, right? Can we prove something like this? Can we prove that every simple connected graph has a coloring of its vertices using delta plus 1 colors so that at least one color class has cardinality at most 1. There is one color that is used at most 1 time. Of course, if you are using fewer than delta plus 1 colors, then some colors are used 0 times, that's okay. But if you are using all the delta plus 1 colors, I want to make sure that one of the colors is used for only one vertex. Then we prove something like that. That would be nice. For any 3 coloring? That's not. But there exists a coloring. Yeah. So it is not true that for an odd cycle every 3 coloring has this property. Right? For example, I can take a 9 cycle. Yeah, I can take a 9 cycle and I can do red, blue, green, red, blue, green, red, blue, green. That works, right? But yes, what we could do is we could just do red, blue, red, blue, red, blue, red, blue, and finally use green at one fellow. That's So it's an exist statement, right? Yeah. Sorry.
It has to be connected.
Connected, yes. Yeah, for a connected graph. Yeah, connected is actually crucial. For any simple connected graph, can we prove this statement? That there is a coloring using delta plus 1 colors such that one color is used at most once. Yeah, think about this. And and observe that connected is actually important. Is that correct? Connected is important. Take 2 odd cycles and see what happens. how would we prove such a statement? So we are trying to do the greedy heuristic, and we are trying to basically do something slightly smarter than the greedy heuristic. Slightly. Good. So what's the problem? When I reach any vertex, when I reach a vertex Vi, I look at all the colors used by the neighbors of Vi that are already colored, right? Amongst the colored neighbors, I check what are the colors that have already been used. And because I have delta plus 1 colors, at most delta will be used by those fellows, and I will have a color free that I will give to this fellow. So, supposing I tell you as far as possible, we will choose a color from this set. We will use the last color only when absolutely required, when we have no way out. Yeah? As far as possible, I will choose a color from the first delta, and I will reserve the last one as a special color. Yeah, which is what we did with the rod cycle. Yeah? Now think about it. Can you find a way to make sure that I never need this last color until I reach the last vertex Vn? Is there a way to come up with an ordering? Can you come up with an ordering so that you never need the delta plus first color until you reach the last one? But then you have no choice, as we have seen in an odd cycle. Think about that. How would you do this? Can you do it? You have a simple connected graph. Why is connected important? What do you know about connected graphs? Do you know some nice properties of connected graphs that could be useful here? Anyone else? Okay, so I'll try to shed a bit more light on what's going on. So when I reach a vertex Vi, one possibility is that all the neighbors have been colored. If all the neighbors have been colored, well, there is a possibility that the degree of Vi is delta, because my graph, for example, could be a regular graph. Like complete graphs are not cycles, by the way. Right? So if I reach the vertex Vi and all of its neighbors have been colored, let's say Vi has degree delta because I have no way to control that, then it is possible that because I am not using any intelligence in coloring, right, it's greedy, right, it is possible that these delta fellows use all the delta colors and now I am forced to use delta plus 1. Right? Do you agree? What would be nice? Sorry? What would be nice? When I reach Vi for I less than n, what would be nice?
If there is at least one uncolored vertex.
There is at least one uncolored. That would be nice. You agree? If when I reach Vi, of course at Vn, I cannot expect anybody to be uncolored because everybody is colored by them. I am the only uncolored fellow. Right? Right? But when I reach Vi for I less than n, if I can guarantee that there is at least one person, one of my neighbors who has not been colored yet, then the remaining can use at most delta minus 1 colors, and then in these delta I have a color available and I will use that color. Of course, when I go to the last vertex, I shouldn't be able to do it because complete graphs are not cycles. Yeah? Does that make sense? So now think about it. Whenever I reach a vertex Vi, I less than n, I want to have at least one of my neighbors not colored yet. Can you somehow make sure this happens? Okay, anyone else? Yeah? Okay, anyone else? Yeah?
Okay, let me try. How does it it's
Okay, anyone else?
how do you
Right, so what do we know about connected graphs? Basically what we want is whenever we reach a vertex vi, there is some neighbor of vi that appears later. Right? Therefore it is not colored. And the only reason for it to not be colored is because it appears later. Right? So can we do that? For any connected graph, can you construct an ordering of the vertices so that every vertex, except the last one of course, has a neighbor that appears later? Right? And whatever your argument is, should crucially use the fact that the graph is connected. Because for a disconnected graph, the statement is false. Right? So what do you know about a connected graph? A connected graph has a spanning tree. A graph is connected if and only if it has a spanning tree. Consider a spanning tree of the graph. Right? A very basic concept, but very useful here. Right? Consider any spanning tree of the graph. You don't have to do any kind of BFS, TFS, all that stuff. All that doesn't matter. The only thing that matters is that it is a spanning tree. Okay, this is my spanning tree, why not? Yeah? It doesn't even have to look like a tree. I can make it look stranger. But it is a tree. Because we are not studying data structures. Like it's a tree. Right, so this is a tree. You all agree? Okay? It's a spanning tree, which means that all the vertices are here. Now can you come up with an ordering with this property? Okay, more show of hands. Maybe until everybody shows their hands. Can you now come up with an ordering for this tree? This is the spanning tree of the graph G. Can you come up with an ordering V1 to Vn so that every Vi for I less than n has a neighbor that has not appeared yet? Yeah? More hands? If you can see it, just raise your hands. If everybody raises their hands, then we'll just not ask anybody. Okay, everybody got it? Yeah? Okay, maybe you can tell us.
Is it like we fix the vertex and then we just go by rows? Like, I don't know how to explain it, but
Make it simpler. So, which is the first vertex you want to pick?
let's say
This fellow?
Yeah, that's fine.
Yeah, can I pick this fellow?
Yeah.
Okay, this is my V1. This is my V1. Now, what is V2?
The either of those, like
Yeah, why not this?
No, we'll just go directly.
Why not this?
We can go directly connected.
I can, but can I also go here? Or will this be a problem?
No, we have to go in such a way that the neighbor.
You sure? This one will still appear later, no?
Yeah.
Can I not put this as
You
V2?
can do that.
I can do this, no? Yeah? Can I do this?
Yeah.
Okay. Now somebody else, the third one.
Basically, they call weeks.
Yeah.
Okay.
That
Which one?
the one on the 4.
Here, this one?
Yeah.
Sure.
Use one.
Which one? What are we doing?
Think about
At
it.
every step, what are we doing?
Picking up.
Picking an arbitrary leaf.
BFS.
Nothing else matters.
Does BFS only know?
The actual order is not that crucial. Just pick a leaf at every step. Take any leaf, delete it. In the remaining tree, there is a leaf. Every tree except K1 has a leaf. K1 doesn't have a leaf. K1 is the graph on one vertex, but leaf is the vertex of degree 1. So keep deleting leaves as you like. This is V4, this is V5, this is V6. The final vertex K1 is my Vn. Observe that because we are deleting leaves at every step, there is a neighbor which has not been deleted. That's it. Yeah? That's the ordering. Delete leaves arbitrarily. Call that ordering V1 to Vn. Vn minus 1. And the last vertex put it as Vn. You are done. So what have we proved? We have proved that the following statement. We have proved that every connected graph has a coloring with so many colors, with the additional property that there is a color that is used at most once. Okay, that's what we have proved. And here we'll take a break. So, G admits a coloring, vertex coloring, using delta plus 1 colors, such so that at least one color is used at most once. You all agree? There is a color that is used at most once. Yeah? Now what we want to do in the next step after lunch is we want to show that this situation happens. I am forced to use the delta plus first color. So basically what I am going to say is these are used as many times. These are used as many times. And this one is used at most once. What we'll do in the next part is that the only ones where we need this fellow, the last color, are the complete graphs and the odd cycles. And you know what will be important? Any guesses what will be important? Once again,
Equal degrees.
Connected.
there is something we used right now.
Connected.
Spanning trees. We will use spanning trees. Okay, that's it. We'll break for lunch. Thank you.
Not George, but where is the George without name? They put proper good name. Not the English spelling.
George Hungarian American mathematician.
George.
Hungarian
American. He's clipped.
the most Hungarian looking.